Yes.
First, when I teach, I always to use this. Does it work? Okay? Okay. Just a moment, otherwise it's dangerous for me, it's too long. Okay, first of all, I would like to thank the organizers for the kind invitation and for the warm hospitality. It's a real pleasure and an honor for me to give a talk in this conference dedicated to such an outstanding mathematician. His book on functional analysis is really a basic reference for all mathematical students all over the world. Well, in this talk I'm going to present the general theory and some recent results on the construction of so-called, say, generalized Feynman-Katz formulae, which are integral representation for a class of for the solution of a class of partial differential equations which do not satisfy maximum principle, including Schrödinger equation. In particular, I would like to show you how the techniques that are traditionally used and applied in the mathematical definition of Feynman path integrals have a wider scope and can be used to construct the representation for the solution of a wider class of partial differential equation. Okay. Well, our starting point is the traditional, very famous Feynman-Katz formula introduced by Mark Katz at the end of the 40s after he attended a lecture by Richard Feynman at Cornell University. Feynman-Katz formula is a very suggestive, in my opinion, representation for the solution of the heat equation with zinc in terms of an integral, infinite dimensional, on the space of continuous path with respect to the Wiener probability measure on it. And it is not only a nice mathematical result, but an important tool in the study of its equation. Indeed, several properties of the equation, as well as of its solution, that are quite difficult to prove by using just let's say, analytical techniques, becomes much more simple when you have in your hand this tool. And according to the words of Mark Katz himself, well, he is more widely known for being the K in the FK format than for anything else he has done in his scientific career. Nowadays, Feynman-Katz formula is just the first and most famous example of an extensively developed theory which connects analysis on one hand, in particular parabolic equations associated to a second-order elliptic operator, to probability theory. In particular, Markov processes described by a stochastic differential equation of this form in such a way that you can construct the representation of the solution of the PDE in terms of the expectation with respect to the distribution of the process. But this largely developed theory, very nice, cannot apply if you consider PDEs that do not have this particular form. For instance, if you simply replace in the heat equation the Laplacian with some, well, integer positive power of it, and you consider a simple equation of this form, which is called higher order heat equation, or if this is most famous, you introduce the imaginary unit in the heat equation here, and you obtain Schrödinger equation. In both cases, we cannot apply the existing theory, and in particular, we cannot write down a representation formula for the solution in terms of the expectation with respect to the distribution of a stochastic process X with real valued paths. Well, the main reason for this no-go result is quite simple. Indeed, the solution of the equation of this form do not satisfy a maximum principle, contrary to the case of the heat equation, but this property would be basically implied by such a representation formula, at least for vanishing potential of good potential B. However, the study of the construction of integral representation for this kind of equations is an important problem, extensively studied since the very beginning, since the 60s, I should say. And in the case of the Schrödinger equation, it is deeply related to the long-standing problem of the mathematical definition of Feynman path integrals. Well, in order to see how to attack the problem, we can look at one of the several possible proofs of the traditional Feynman-Katz formula and see what works in the case of the heat equation which cannot work for Schrödinger or higher order equation. I consider the proof based on total product formula, for instance, presented by Nelson or by Barry Simon. To simplify the notation, I consider the one-dimensional case, but the argument can be extended to arbitrary dimension D. Well, by the famous total product formula, the semigroup on the Hilbert space R2 of the real line generated by the operator sum of an operator A, which we assume to be the generator of a contraction semigroup on L2. So at this stage, A can be either the Laplacian, and we will obtain the heat semigroup, or some higher power of the Laplacian with a suitable coefficient, and we get higher order heat-type equation, or the Laplacian times the imaginary unit, and we get the Schrödinger equation. And then we consider a multiplication operator V associated to a potential V, which for the sake of simplicity we assume continuous and bounded, yeah, but this assumption can be relaxed. This is not the key point here. Now, by total product formula, the action of the perturbed semigroup over an initial vector U0 can be given by almost everywhere x in R as the limit of a sequence of this form where the free semigroup and the semigroup generated by the multiplication operator act independently. Now, if you use the fact that the free semigroup is described by a kernel G, and we insert this particular representation using the fundamental solution in this sequence here, we obtain that the solution of the perturbed equation with the potential can be expressed as the limit of a sequence of finite dimensional integrals of this form just by using this representation. And now the key point comes, because now we can try to look at this expression as the cylindrical approximation of an infinite dimensional integral over the space of real valued paths with respect to the distribution of a Markov process which has G as probability transition density. And by taking the limit, we obtain what we wanted to obtain, this Feynman-Katz type formula. But this last step is allowed provided this process X exists. Well, in other words, provided that we are able to construct on the space of real valued paths a measure mu whose value on the cylinder sets is given by this expression, this formula, where G is again, the fundamental solution of the unperturbed equation. Now, the traditional case, the equation G is well known. is the well-known Gaussian probability density, Kolmogorov existence theorem for the projective limit of a consistent family of probability measures gives us the existence of such a measure mu. But when we consider Schrödinger equation or the higher order type equations, something changes abruptly. In particular, G is no longer real and positive and can no longer be recognized as the density of a probability measure. In particular, well, in the case of the free Schrödinger equation, it is well known, it has this form, it is a complex function which has an oscillatory behavior. In the case of high-order type equation, G can be still computed in terms of this Fourier integral, and it is rather easy to study its properties. One can see that it is a smooth function. It is a 1, but it is real but not positive. Indeed, by an application of the saddle point method to the study of this integral, you can see that this function, where the difference between x minus y goes to infinity, has an infinite number of oscillators. So it changes signs an infinite number of times. And in this formula, it has to be regarded as the density of a sign measure. When we consider Schrödinger kernel, we construct here complex measure. Now, Kolmogorov existence theorem has been generalized to the case of sign or complex measures instead of probability ones by Eric Thomas in 2001 in the best generality we can get, so in the framework of projective systems of measures. And according to Thomas' result, what is fundamental for our discussion is the following necessary condition which allows that a consistent family of sign or complex measure admits a sigma additive projective limit which has a finite total variation. So we need a uniform bound on the total variation of the measures belonging to the consistent family. This is a necessary condition for the existing of the limiting measure. And if we apply Thomas' results to our particular case, where we have a consistent family of measures which are complex or signed, depending whether we are studying Schrödinger or higher order type equation, we can simply construct the total variation of the family of the measures and see that unless G is real and positive, but this is not the case, this total variation is not bounded. It increases exponentially with the number k of the time instant we are considering. This means the following. If we consider Schrödinger or higher order type equation, we cannot construct a process which plays exactly the same role that the Wiener process plays for the heat equation. Indeed, according to Thomas' result, we see that if the construction of probability measure or infinite dimensional spaces might be, say, technically difficult in some situation, in most cases, the non-trivial one, the interesting one, the construction of sign or complex measure is impossible. If you want good properties of this measure, if you want finite total variation, and if you want sigma additivity, of course. And Well, this is a noble result in some way because we cannot define generalized Feynman-Katz formula in terms of an integral, Lebesgue type integral, with respect to a well-defined sigma additive measure. And according to the words of Richard Feynman, one feels at this stage as Cavalieri must have felt calculating the volume of a pyramid before the invention of the calculus. However, despite this difficulty, the problem is extensively studied, and in order to solve it, in order to handle this lack of a measure, we can try to change a point of view and try to replace the concept of integral with respect to measure with the more general concept of a linear continuous functional on a suitable domain, a space of, say, integrable function. By Ritz-Markov theorem on suitable topological spaces, X, which has to be Hausdorff locally compact, there is a one-to-one correspondence between linear continuous functionals on the space of functions which vanish at infinity and a complex measure with finite total variation, but on different topological spaces and on an infinite dimensional setting we cannot require local compactness, or with different classes of integrable function, the concept of functional is more general and can be used to construct an alternative integration theory in infinite dimensional in all the cases where a measure cannot exist. This is the underlying idea, which has been developed by Sergio Albevaria and myself in a couple of recent papers where we try to give a unified view of probabilistic and oscillatory integration in infinite dimensions by introducing the concept of projective system of functionals instead of projective systems of measures. Concerning the particular problem we are studying now, this theory assumes the following form. Well, we are given this consistent family of measure constructed in terms of the fundamental solution of the Ampère-Taub equation, and in order to build a Feynman-Katz type formula for the solution, we want to construct a linear functional L on a suitable domain which has this property. We ask the domain to contain cylinder functions, that is, functions which depends just on the values that the path gamma attains at a finite number of time. And we require that the action of the functional L on functions of this form here, which are finite base, must be exactly given by a finite dimensional integral with respect to one of the measures belonging to the consistent family. Now, if this consistent family of measures doesn't have a projective limit, as in the case we have seen, this function we know that cannot be of the form integral with respect to a measure, but it can still be defined, and this is the case of the example I'm going to show you in a while. Well, nowadays you can find in the mathematical literature several implementations of this program, that is, several different possible construction of generalized Feynman-Katz formula either for the Schrödinger equation or for the higher order E-type equation. I would like to point out that this list is far from being complete. I have just written here a few approaches, but there are more, and Professor Smoljanow and his school can surely give some contribution and can surely add something here, and I will be glad to discuss with them. Okay, just to give you an overview briefly, the first approach introduced, I think, was by analytic continuation technique by Cameron in the case of the Schrödinger equation, and by Funaki in 1979 in the case of high-order type equation. Then there are also approaches in terms of infinite dimensional distribution theory introduced by Cécile de Witt-Moret. But this approach reaches its best mathematical form in the framework of Ida white noise calculus, and it has been recently applied by Rémy Léandre to this kind of PDEs. Then there is a sequential approach extensively developed by the Japanese school, which is, I think, closer to Feynman's original approach. And today I will discuss in some detail the Fourier approach, the Fourier transform approach, which has its roots in a couple of papers by Ito in the 60s, and was further developed by Albererio and our Krohn in the 70s, and applied to the mathematical definition of Feynman integral, as well as to the study of their asymptotic behavior, semi-classical asymptotic behavior when the Planck constant h bar goes to 0. Let me say that this line of research is still active, especially for what concerns the right-hand side of these slides. Indeed, recently several papers appeared on probabilistic in a larger sense representation for the solution of this class of equation. For instance, Professor Kumano-Go, by means of his technique, Stefano Bonacorsi and myself by means of stochastic processes on the complex plane, and even Terry Lyons in 2009 conjectured that the rough path theory could give some hints in the solution of the problem. Today I will speak about, in the last part of the talk, of some recent results I have obtained in this paper, where I just generalize traditional, well-known now, infinite dimensional Fresnel integral of Albererio and Krohn, and apply them to the representation of this kind of equation. Well, what are infinite dimensional Fresnel integral? The main idea is rather simple and relies on Parseval equality, which on a finite dimensional vector space Rn allows to write down an expression of this form. It allows to express a Fresnel integral of a function capital F, which is Fourier transform of a complex measure mu f, in terms of integral of this bounded function with respect to the measure mu f associated with f by this relation. Now, this is the key formula that Ito before and Albererio and Krohn use in the extension of this object to the case where Rn is replaced by an infinite dimensional real separable Hilbert space H, because even if when the dimension m goes to infinity, the left-hand side of this equality loses meaning, we no longer have the back measure and this normalization constant blows up, the right-hand side is still meaningful. It is still a well-defined integral with respect to a measure of a continuous bounded function. And Albererio and Krohn choose the right-hand side as the definition of their functional So the infinite-dimensional Fresnel integral of a function f on an Hilbert space H, which is Fourier transform of a complex measure, is exactly defined by the right-hand side of this expression. It is a simple idea, but it is really fruitful because it was applied to the mathematical definition of Feynman integral as well as to their study of the semi-classical asymptotic behavior. Now I'm going to show you that this object is just a particular case of a more general one. Now let us consider, instead of an Hilbert space H, a Banach space B, which is real separable, and let B star be its dual. And let us consider the vector space of function f defined on B star, which have this form. They have to be, well, Fourier transform of a complex bounded measure mu f on the Banach space B, where this bracket denotes the dual pairing. Now, f of B is a Banach algebra where the product is the pointwise one, and the norm is defined to be as the total variation of the measure associated to the function. And given a phase function phi, which has to be continuous and with non-positive real part, we define the infinite-dimensional Fresnel integral on B star with phase function phi as the functional with domain fb, which is given by, well, this expression. So the action of the functional over a function f, a Fourier transform of measure, mu f, is given by the integral with respect to mu f of the exponential of the phase function phi we have chosen. And this object has some nice properties. It is linear and continuous in the topology of the Fresnel algebra f. It is normalized and generalizes infinite-dimensional Fresnel integrals in the sense that when B is an Hilbert space and the phase function is just the square of the norm of the vector multiplied by this imaginary coefficient, we still obtain the infinite-dimensional Fresnel integrals of Alberegger or Krohn. Now, this generalization is meaningful provided that we can give some meaningful application of it. And this is a particular case. So let us consider this I-order type equation where P is a positive parameter that we take to be greater or equal than 2, and alpha is a complex constant. We consider the Banach space of absolutely continuous path, gamma, with fixed endpoint and weak derivative in LP, and now with this norm. The dual space BP star is naturally isomorphic to BQ, where P and Q are conjugate by this relation, and the pairing is given by this expression. And we can still consider, well, the Fresnel algebra on BQ, that is the space of function of this space, which are Fourier transform of a complex bounded measure mu f on BP. And eventually we consider this particular phase function, which is actually proportional to the p power of the norm of the space we are considering, where we have to require some constraints to the constant alpha in such a way that the real part of this phase function is non-positive. Well, now, we consider the functional, the infinite-dimensional Fresnel integral with phase function phi p as the functional on the Fresnel algebra defined by this expression. Okay, it is well defined and enjoys all the properties discussed so far, but this is the key lemma. This key lemma is actually the main result because it shows that this functional does exactly the job that we wanted it to do. Indeed, if we consider on BQ cylinder function of these forms, it depends only on the value that the path attains at a finite number of times, and capital F is a function from Rn to C, which is a Fourier transform of measure. Then we can prove that this small f belongs to the domain of our functional, to the Fresnel algebra, and its infinite dimensional Fresnel integral with phase function phi p is given by exactly what we wanted to obtain. So it is the integral of capital F with respect to the finite measure on Rn, which is constructed by using the fundamental solution of this higher order type equation as a density. And this is the key lemma which allows the proof of what we were looking for, a generalized Feynman-Kat formula. Indeed, we consider now the perturb problem. And if we assume that the initial datum U0 as well as the potential V are Fourier transform of measure on the real line, then we can prove that this particular function on BQ belongs to the Fresnel algebra, so to the domain of the functional, and the action of the functional L phi on it gives exactly a solution for this particular initial value problem. Well, this is not the end of the story, but it is the very beginning. Indeed, this line of research left several problems still open. One of the most important ones, in my opinion, is the extension of the class of potentials which can be handled in this. Indeed, according to this result, we can just consider potential which are Fourier transform of measures on the real line, which is quite a poor class. These functions has to be continuous and bounded, but from several points of view, it would be interesting to be able to consider unbounded potentials. Well, some partial results in this direction have been obtained by Sajjad Bavaria and myself in 2005 concerning Schrödinger equation, but the problem of higher order type equation is still completely open as far as I know. Another interesting line of research is the extension of this kind of result to the case, the order of the derivative, spatial derivative p, is not integer, but it is fractional. Recently, in collaboration with Stefano Bonacorsi and Mirko Dovidio, I propose a probabilistic representation for the solution of this class of equation for any real positive order p, but those techniques are not easy to generalize to the case where we add a perturbation potential. This is very difficult, so this is still an open problem. And eventually, as you have seen, the techniques I have described relies upon a Fourier transform approach, so on Fourier analysis. And so I think that it would be interesting to investigate whether we can obtain analogous result in the case where the real line, or more generally Rd, the Euclidean space, is replaced by a finite dimensional Lie group. And that's all. I think I can stop here. Thank you for your attention.
Questions? Not, thank you very much. We'll come again. And we have a final